Hello. In this video, I want to talk about why heating an object will slow time down in the object. So that may seem surprising, but when you think about it a bit, when we heat an object, we basically have the molecules that are in the object go faster. And we know that due to relativistic time dilation, if an object goes faster, well, time will slow down for that object with reference to a stationary observer. So basically, if I'm in the room here and I heat my chalk, theoretically, the molecules in my chalk will go faster and time will slow down in the chalk. So we may say, well, that's how theoretical, and we will calculate what would be the size of this effect approximately in this video. And we would say, well, you really can't observe that experimentally. In theory, it should happen, but in fact, we can see that in experiments. So this video is about this effect, and let's see how it goes. So first thing we need to think about is, how do objects go faster when we heat them? Well, just back of the envelope calculation, just to have an idea of the order of magnitude we're dealing with, we know that due to statistical mechanics, every degree of freedom in an object that will be heated has some energy in each degree of freedom. So what do I mean by degree of freedom? I mean, the degree of freedom could be, for example, the speed at which a molecule goes in a gas or in a solid, and also in the solid we have degrees of freedom due to the fact that the molecules can be modeled as being linked together by springs, which are basically the intermolecular forces. And there's a term in, for example, 1/2 a constant times the distance squared for small amplitude, and this term also contributes to the degree of freedom. But let's forget about all this and just let's concern ourselves with only the degree of freedom related to speed. And there is a theorem in the statistical mechanics that states that for every degree of freedom that has a squared term in the energy, there is about a half kT. So the energy in each degree of freedom is equal to half times the constant, the Boltzmann constant, times the temperature. And well, in a solid, let's concern ourselves only with the speed, because that's what this video is about, is how fast do things go and what happens with the relativistic time dilation in these effects. Well, we know that the energy for each degree of freedom is equal to about half the mass times the speed squared. Then if we look at this, we see that the speed goes to as the square root of the temperature. Okay, that gives us an idea. Now, what is the speed of a molecule in a solid or in a gas at room temperature? Well, of course, the speed has a speed distribution. Some molecules or atoms would go faster, some would go slower. But an order of magnitude is that at room temperature, we have speed is of the order of 300 meters per second, approximately. Could be, you could put in 4, you could put in 350, depends on how you define the speed and so on. But I mean, I will use 300 meters per second because, of course, the speed of light is approximately equal to 3 times 10 to the 8 meter per second, and then calculations become very easy. So we have a speed of around 200 meters per second. What is the time dilation due to this speed? Well, we know that the duration of a time interval in a reference frame prime compared to a fixed reference frame is equal to a factor gamma times the time difference in the first reference frame, which is equal to 1 over square root the 1 minus v squared. So v squared is the speed of the second reference frame with respect to the first one, over c squared delta t. And now, well, if we know that if x is much smaller than 1, 1 plus x to the alpha, and the exponent is about equal to 1 plus alpha x. So using this, because 1 minus v squared, so c squared, 1 over the square root of this quantity, is equal to this quantity at a minus to the minus 1/2. So we see that this is about equal to delta t times 1 plus v squared over c squared over 2. There's a factor of 2 here. Okay. Now, if v is equal to 200 meters per second, and c squared, c is equal to about 3 times to the 8 meters per second, we see that in our case, delta t prime is about equal to 1 plus 10 to the 2 over 10 to the 8, because the 3's will cancel out. There's a 2 here. Delta t, which is equal to 1 plus 1/2 of 10 to the minus 12 times the original interval. So that tells us that the time dilation will be of the order of 10 to the minus 12, which is really, really small, and which will make it really surprising that we can measure these effects actually in a lab. And we will come to that. Another thing that we can think about is if we want the time dilation to double, so we're going to remove this factor of 2 here, what do we have to do? Well, we would have to have the v squared term doubling. And so if we want to have this v squared term doubling, so that we can double the effect, we can take the square on both sides, and to double v squares, we have to double the temperature. So if we start from room temperature, about 300 kelvins, and we go to 600 kelvins, then this effect should double. So we need 300 kelvins or Celsius to double the effect of the time dilation, to have an effect of about half of 10 to the minus 12, which means that changing by a few degrees the temperature of an object will have an effect that it's about 10 to the minus 16, 9 to the minus 15 difference in the time dilation, which is really, really small. It's really surprising that this has any relevance in any situation we could encounter on Earth. But surprisingly, it does, and that is the object of the next board. Okay, so how can we observe this effect? Well, one way that it can be observed is by using what is called the Mossbauer effect. Basically, the Mossbauer effect is a situation in which you have some nuclei in a solid that can emit gamma radiation. So we know that if we have some atom that stands in the empty space and there's a gamma ray emitted in this direction, to conserve momentum, the atom has to recoil in the other direction. And of course, this will take a bit of energy from the gamma ray, so that the gamma ray will in fact have less energy than it would have if we could somehow have the atom stay in place. Now, the Mossbauer effect is an effect in which some atoms can just emit gamma rays, and these gamma rays can be absorbed by other nuclei. And the problem is, of course, that if you have this atom here and you emit a gamma ray and you want it to be absorbed by the nuclei, well, the frequency here is not the same. It would be the same if you want some atom to absorb some light. It absorbs light at some frequency, but somehow you don't shine the right frequency on the atom, well, the light will be not absorbed, it will go through. So you would say, in theory, it shouldn't be possible to have this resonance, emitting the gamma ray and absorbing it in another piece of the same material, spaced apart, because of this recoil. But it turns out that in some crystalline solids, the atom remains in place. So why does it not recoil? Because this atom in the solid is coupled to the crystalline lattice of the whole block, and basically you're not trying to recall an atom, you're trying to recall the whole block. And if you do that, the mass is much larger, and basically there will be almost no energy dropped into the block, and the gamma ray will basically have the same frequency as it would have if the atom was stuck in place with glue. So if you do that, you can have some gamma rays that are emitted, and you can absorb them later, and you will have this resonance, and you can measure the quantity of gamma rays that are absorbed, the quantities that go through, and so on. Now, where does our temperature difference come into effect? We've seen that if we heat a solid, then the temperature of the solid will increase, and this will increase the speed of the molecules in the solid. And if the speed increases, then time slows down. If time slows down, then the frequency of the gamma ray that's emitted will be lower. It's basically the Doppler effect, the relativistic Doppler effect that we're observing. And if this frequency goes down, then it shouldn't be absorbed. And this can be seen if you have a Mossbauer spectroscopy apparatus and you eat one of the pieces in the apparatus, you will see that the resonance will tend to disappear. Now you would say that's all very interesting, and is it observed in the lab? Yes, it's observed. There are recounts of people who would work these apparatuses, these Mossbauer effect spectroscopy devices, and they observe that effect. If you eat the device here, you will lose the resonance. And a practical application of this, well, kind of practical, is seen is the Pound-Rebka experiment that tried to look at the relativistic time shift in a gravitational field. So this will be on the next board. I will explain why people had to be very careful in this experiment, especially because of this effect. So what happened in the Paul-Rebka experiment? A result of general relativity is that time will slow down in an intense gravitational field. Well, this means that if you have a device with some piece of material here closer to the Earth and up, a few tens of meters up in the air, another piece of the same material, and you try to measure the Mossbauer effect in between the two, well, time will slow down here. Here we're talking about gravitational effect, so we're not talking about temperature yet. Time will, in theory, be slower here than here, and you should observe an effect. It should add an effect on the resonance. So I would not get into all the details of how they measure that. It's a bit complicated, but basically just the general idea is that to see what the effect is, they have this thing, or one of the two move up and down. And because the Doppler effect due to the up and down movement at some point will cancel out the relativistic effect due to the higher gravitational field, you will obtain a certain resonance only at certain moments in the up and down movement, and you can do some data acquisition over some long time and see that in fact you observe this gravitational effect. And the gravitational effect here, the time dilation is about of the order of 10 to the minus 15. So it's very, very, very small effect. How does our temperature effect cause problem in this experiment? Well, since the time shift you're trying to observe is the order of 10 to the minus 15, and we saw that for a few degrees of difference in temperature, you would expect the heating of the device to have an effect of the order of 10 to the minus 15. We saw that to under 300 degrees, you had an effect about 10 to the minus 12, or half of 10 to the minus 12. So it's the same order of magnitude. And indeed, when they did the experiment at first, they had some issues. They had problems. They couldn't reproduce the right result. They were in the right ballpark, but their result did not agree perfectly with the relativistic prediction. And it was observed by one of the experimenters or a colleague of them that, well, these two things don't necessarily have the same temperature. And if they don't have the same temperature, then there will be some Doppler shift because of the speed of molecules in the two blocks that are used for the Mossbauer effect experiment. And this will cause issues with the accuracy of the experiment, because now you have another time shift that's not purely due to the gravitation. And indeed, when they balanced out the temperature between the two blocks to make sure that they were within a few fraction of the degrees from each other, the accuracy of the experiment increased greatly. So all this was inspired by a post in the Physics StackExchange forum. I will put a link to the post in the description, and I will also put links to the Mossbauer effect and the Paul-Rebka experiment that we can find on Wikipedia in the description. So tell me in the comments, do you have any other situations in which relativistic effects can be detected in which you would really not expect to see them? And that's it for today.